Homework Hotline, what is your emergency?
Hello, welcome to the Homework Hotline. This is the show where you ask the questions and we walk you through the steps to a successful answer. I'm Becca and I'm a math teacher.
We have had a pretty long hiatus from the show, but now we're back for the spring semester of 2016. My name is Nathan and I'm also a math teacher. Same as last semester, we were here every Tuesday and Wednesday from 4:30 to 5:30 p.m. You can give us a call at 720-424-1666. We love getting your calls. It's a little bit more helpful to help us answer your questions.
Definitely. And I'm Sam. I'm the science teacher, so I'll be answering your science questions.
You can watch our show in several different ways. For live broadcasts, you can watch us on Comcast Channel 22 or go to livestream.com and search for EG Homework Hotline. If you'd like to see some of our past shows, you can watch us on YouTube by searching for DPS TV Homework Hotline.
And the Homework Hotline is sponsored by Contemporary Learning Academy and Emily Griffith High School. Becca and I teach at Emily Griffith, and Sam over here teaches at Contemporary Learning Academy.
Yeah, that's right. Today on the show, we're going to honor one of the current events in town, the Western Stock Show. This is a 110-year-old tradition here in Denver, and so our trivia question and Facebook discussion will be themed around it. Lily, an EGS HS student, will be leading us in the trivia questions. Lily, you want to tell us a little bit about yourself and that trivia question?
Hi guys, I'm Lily and I'm a senior at EJHS this year. The Homework Hotline loves to be accommodating to those of you who like to turn in your questions on social media, and I help get those questions over to our teachers. Also at the top of each show, I will be the trivia queen, so I will ask you guys a trivia question, and I hope by the end of the show you will call in with the correct answer. If you call in with the correct answer, you will win a prize, and the trivia question can also be on any subject, but today is an animal question. So the trivia question today is, which state has the most dairy cows? And we will answer that at the end of the show.
So if you have an answer to a trivia question or homework questions, you can call us at the phone number. It's on the top right of your screen. Nate gave it to you earlier. But we also have a few other ways that you can get in contact with us. If you would prefer, you can get in contact with us on social media, Facebook and Twitter, at EG Homework. You could also text us at the phone number on the bottom right. It's 970-680-3771. Or you could even email us at homework@emilygriffith.edu. We prefer call-in questions just because we can really make sure that we help you the best with those, but you've got all the options in the world. So that's how you can get your questions in or answer that trivia question Lily showed us. So we probably have a lot of questions from over our break. So let's go to social media with Lily and see if we can get some of those answered.
The first one asks, how do you write 5.76 times 10 to the fourth power in standard form?
All right, I'm writing your number down. Times 10 to the, what power was it?
Fourth power?
Fourth power. Mm-hmm. Great. Okay, I can answer this. If you cut to my screen, I'm just better explaining things when I've got a visual anyway. So this is the number that was given to us through the Twitter question. And it was asked, how do we write this in standard form? Now, the form that this is in right now is called scientific form. And scientific form it's really helpful when you are expressing really large numbers, like if you were to talk about millions or billions or trillions or anything larger than that, where you might have to write a lot of zeros. Or really small numbers. And in science, we work a lot with really large numbers. Think of, outer space. And we also work with really small numbers a lot. So this is called scientific notation. It's a way of abbreviating long numbers. Now, it works off the premise that anytime you multiply a number by 10, what's happening is you're moving your decimal. And let me explain something really fast. A lot of times, elementary school teachers may teach this way, and this would be incorrect, but this might be something that you've heard before. Anytime, so I'm making a generalization right now, and this is an incorrect statement, but anytime you multiply a number by 10, just add a 0. It's a common way that elementary school teachers might teach. You might have heard this before. That's not true. It does work in these cases. Oh, 6 times 0 is 60, 45 times 10, 450. This works really well for whole numbers, but what happens when you get a number like this, 5.0 times 10? I can't just add a 0 to it. It's not true. So that's kind of a generalization that's not true. What we're really doing when we multiply a number by 10 is not just adding a 0, we're moving the place value. So when I'm taking 5 times 10, what I'm doing is I'm moving that decimal and I'm moving it to the right a place value. So 50. And we put a 0 there. Sorry, we put a 0 in this place, in this little spot where our decimal point is, as a placeholder to show that we've now moved it over a place value. So when we're multiplying by 10, we're moving our decimal over a place value. In this case up here, what I just circled, that says I'm multiplying 5.76 by 10 4 times. So what I'll be doing is not just moving my decimal one spot, but I'm actually going to move it 4 spaces, because I'm multiplying it by 10 4 times. So I'm going to take my decimal point, I'll move it to the right, 1, 2, 3, 4. It's now going to be in this spot. I need a placeholder, 0 placeholders, in order to kind of mark those place values, and that's my number. This is standard form of the number in scientific notation that is written above. And the concept is just based on when you multiply by 10 or divide by 10, you're just moving your decimal to the left or to the right. Hopefully that makes some kind of sense as to how it works.
Could I ask a follow-up related to
Sure.
it? So scientific notation is really important to me. I try to hit it almost every unit that I do in my class, or almost every semester, I guess I should say, because it's so applicable in science. One thing that my students struggle with is with bigger numbers, they're pretty good. So if we say, like we're looking right now at Avogadro's number, which is 6.02 times 10 to the 23rd power, and they can do that. They will move the
23
thing
times.
23 times and get this gigantic number.
Gotcha.
What we struggle with sometimes is if we're talking about a small thing, we would end up with a number, so for example, we might end up with a number if we're looking at the size of a bacteria. We might find that a bacteria cell is 2.3, let's say, times 10 to the negative 6 meters.
Okay.
That might be how big it is. And when my students see that negative exponent, I so often am getting negative numbers as the answer. So would you maybe explain what a negative exponent is going to do in scientific notation?
A negative exponent, and that just has to do with the understanding of what a negative exponent is. A negative exponent, so if a positive exponent is multiplication, repeated multiplication, you can think of a negative exponent as repeated division. And so if you're doing, for example, and you can look on my screen, I have the number that you expressed, 2.3 times 10 to the negative 6. You can think of this as dividing the number by 10 6 times.
Right.
And so if you're dividing a number by 10, you take away a 0 or move your decimal to the left. And so really that understanding, I think, is in, or misunderstanding is in knowing what a negative exponent actually means.
Right.
And it just means repeated division,
Right.
whereas a positive exponent means repeated multiplication.
So what I try to tell my students is even if there's a negative exponent, it's going to be a number smaller than 1, but not less than 0.
Yes, and I might show them this example. So I'm just putting on the board or on here, just maybe to show them like a pattern, for example. If you show them, okay, 2 to the 4th is 2 times 2 times 2, 4 times. 2 to the 3rd multiplied by 3 times, and then just show them this pattern of, okay, well this is 1, and now this is 1/2, and this is 1/4, and these are all decimals, and these are all smaller numbers because we're doing division.
Gotcha. Thank you for that.
Yeah, that's a good question. All right, do we have other questions to answer, Lily?
We do. They ask, how do you balance this equation? I am not familiar with these fancy
It's okay.
science
Why don't you
terms,
let
so-
me read it? And Nate, would you
Yeah.
mind helping me out by drawing it on your
Exactly.
screen? So you can just draw the chemical symbols, and I'm just going to read them to you as they're written. Okay. So you've got AS plus, and if you do me a favor, just leave a little space in front of each of the
Okay,
chemicals.
I'm leaving
okay?
a Trying to do the underline like they did.
Excellent. So plus NaOH
Okay.
yields, so an arrow going to the right, yields Na3, and that's a subscript 3, a little 3 down below.
Okay.
AS, O, and then subscript 3 again, plus H2.
All right.
Okay,
Got it all
so if I was going to read this as chemicals, it's astenine or astenine plus sodium hydroxide yields, I am not actually sure what that chemical is, and hydrogen gas. But it's the chemical that I don't know. It's some kind of a compound made of sodium, astenine, and oxygen. So what we're trying to do here is, this is actually something I'm teaching right now in my chemistry class, so this is kind of perfect. The idea here is based on what's called the law of conservation of mass. And the law of conservation of mass states that within a closed system, so if you're not losing anything to the outside world, if you run a chemical equation, whatever ingredients you put in, the mass of the ingredients put in should be equal to the mass of the ingredients that are output. And so from a simple perspective, what we want to do is make sure we have the same number of elements on the left as we do on the right. So the first thing that I'm noticing as I'm looking at this is, on the left side, I have sodium hydroxide, which has 1 sodium, 1 Na. But on the right side, I have 3 sodiums. So that means that my equation currently is not balanced. And what we're going to try to do is balance it to make sure we have the right number of chemicals of each type. Okay, so the first thing that we're going to do is, since I notice that there are 3 sodiums on the right, but only 1 on the left, is I'm going to put a 3 in front of the NaOH, the sodium hydroxide.
So right there.
Yes, indeed.
Right.
So that would mean that we're going to have 3 parts sodium hydroxide to end up yielding whatever we need. Now this is great because it means that if I'm looking, okay, so on the left, I notice that I've got 1 As, 1 astenine, and on the right, I've got 1 As, 1 astenine. So that's perfect and balanced. If I look on the left, I've now got 3 sodiums, and on the right, I've got 3 sodiums. So things are looking good. But when I multiplied that NaOH by 3, I also multiplied the O and the H in addition to the Na. So now I have 3 oxygens and 3 hydrogens on that left side. Now if I look at this compound, Na3AsO3, that's kind of perfect because it has 3 oxygens as well. So just by doing that one move, I've almost balanced this whole thing. I have 1 astenine on the left, 1 astenine on the right. 1 sodium on the left, or sorry, 3 sodiums on the left, 3 sodiums on the right. 3 oxygens on the left, 3 oxygens on the right. What's missing now is we've got 3 hydrogens on the left, but only 2 hydrogens on the right. And so what we want to do is get these balanced. And so what I would do is this. I would say, okay, what number could I multiply 2 by, since there's 2 hydrogens on the right, to get 3?
That would be 1.5.
That would be 1.5. So let's do that, if you don't mind. Let's write 1.5.
Oh, are you allowed to do that?
Oh, so technically no, and let me explain why. So, okay, normally when we're talking about these kinds of chemical formulas, we're talking about large quantities.
Right.
So the way I would read this now that Nate has it set up, and this is actually correctly balanced with one minor mistake. So the way I would read this is I would say, since there's no number in front of the AS, I would say 1 mole of astenine plus 3 moles of sodium hydroxide yields 1 mole of this chemical Na3AsO3 plus 1.5 moles of H2 gas. And that's doable because I can measure out 1.5 moles of hydrogen gas. But one of the problems is we often think about this as individual molecules. So an individual molecule, 1 molecule of astenine, combines with 1 molecule of sodium hydroxide to yield one molecule of these, and then we can't have 1.5 molecules of H2 gas. That's a problem. So what we do now, just to make them all whole numbers, is we're going to do whatever we have to that 1.5 to make it a whole number, and we'll do the same to all the rest. So what I'm really going to do is multiply all of these, and these numbers ahead of the chemicals are called coefficients. And so I'm going to multiply each of the coefficients by 2.
So guys, if you pay attention in math, you can also understand chemistry.
And I reference all the time, I say all the time to my students, you know, when we're thinking about these coefficients, think about your equations that you're doing in math. All sorts of different quadratic formulas, for example, are going to have variables with coefficients, right, often.
Right.
And so it's that understanding of, if I know what a coefficient is in math, I can often be successful when that vocabulary comes at me in science.
That reminds me to emphasize that then.
Please do. We science and math teachers should be coordinated.
But I really need to emphasize that coefficients exist also
In other places.
other places.
Yeah.
A coefficient is not just a number
Not
in
just
front of
a
a
wonky
variable in
math
math.
term.
Yeah.
So anyways, to get back to the final answer,
Sorry.
we would end, no, that's perfect, thank you so much. So the final answer, we multiply each of the coefficients by 2, so we would end up with 2 AS plus 6 NaOH yields 2 Na3ASO3 plus 3 H2.
Now, if you're
So-
writing this out, like working the problem out, would you do it, and I'm just guessing here because I haven't seen this in a very long time, would you do it similarly like how you do it in algebra?
So you don't
Kinda like
actually,
this,
so you
or-
would, yeah, my students actually were asking me literally about this today. They said,
Yeah.
shouldn't I put the chemical in parentheses if I'm going to multiply? And we don't do that since the chemical
Okay.
formulas don't have
So I'm gonna erase that.
numbers. The only numbers in a chemical formula is the subscript. And in a
Right.
well-written chemical equation, it should be very easy to distinguish coefficients before
Okay.
with subscripts within. So we don't.
So
tend
would
to
I
do that.
just rewrite this as like 2
Yep.
AS plus 6, kind of just like that?
That's exactly the case.
I mean, the equality rule, this is just like an equation.
Okay,
I
so-
mean,
Right.
it's like,
So systems of equations are the normal way to solve this. With most chemical formulas, it's easy enough to just look at them and sort of go back and forth and figure out what do I need to add to one side to make it equal the other. But were you to have a more complex formula, and I should bring one in as an example, you can use systems of an equation.
I never did that in high school, but
solve
that is
this.
so cool.
So one of the issues we run into, right, as science teachers is we say, okay, is it worth taking a week to teach systems of equations?
No.
And it's usually not. So we teach shortcuts,
Well, they
hoping that
should
they're
know
going
it
to
in
get.
math.
They should, right? So they should be learning it in math, right? One of our great challenges, I think, is connecting all these different disciplines.
Yeah.
So hopefully that made sense.
I
That was
love
kind of a
that.
long-winded
That's cool. That's really
explanation.
cool.
Yeah.
Very, very cool. Well, I think we have time for another social media question.
Killer.
Lily, would you like to share?
So we have in parentheses 5a plus 4 minus
Wanna do it?
in parentheses 5a plus 3. So
Yeah, I can take this one. I'm
I
gonna
guess
go
we're
ahead and,
simplifying, right?
yeah, it looks like
Sam?
it didn't mention, but typically
Thanks, Lily.
what you're gonna see here is I'm making the assumption that this is gonna be a simplification, and the main reason is you don't see any equal signs. There's no equality. There's really nothing to solve for. So what we typically would think about here is just using our order of operations, PEMDAS, and kind of walking through and just simplifying and combining our like terms. So the first thing we need to look at is there anything in parentheses that we can simplify? In this case, I don't have any like terms inside the parentheses. I have 5 times a plus 4. These aren't like terms, we can't combine them. So I'm going to leave those alone, but I'm going to look at the next expression in parentheses. 5a plus 3, again, we don't have any like terms in there, so we just have to leave it alone. So parentheses, nothing to do there. Exponents, we see there's no exponents. And actually, I'm just going to kind of walk through this. So since we can't simplify inside the parentheses, I like to just get rid of the parentheses now. Now, this is kind of what I notice trips up a lot of students, this negative here.
That's the spot.
Right. This negative, if you want to think about it as like a -1 times this, it kind of helps. But this negative needs to be distributed to everything inside the parentheses.
Because you're saying minus.
Minus
Everything.
everything inside, not just
Yeah.
minus 5a, minus everything. So typically what I see as a negative might be applied to the first term, but it's forgotten in the second term. So we need to think about distributing this negative to everything. Right, so we're going to do -1 times 5a, and we're going to get minus 5a, and then a -1 times a positive 3, and then minus 3. So all we do from here is just combine our like terms again, and like this equation, there's not too much going on, but sometimes when these expressions get really big, and if you're starting with this, they're going to get bigger as more of a challenge. It's sometimes helpful to circle your like terms to make sure you're not forgetting anything, and then combining them from there. So 5a minus 5a, that's just 0. If you have 5 of something and you take away 5 of the same thing, then you have nothing. So then we're just left with this positive 4 and negative 3. And you simply have 4 minus 3, which is 1. So again, I think the kind of the key things here are be careful, especially when you have negatives, parentheses, make sure that you're distributing. And also, don't rush these problems because that's where you see a lot of mistakes, everybody skipping steps. But,
And do things, I like that strategy where you showed circling them or drawing a square around them. Have kids used highlighters before, different colors for like terms. So whatever it is that you have to do, to help yourself, but that's good strategies, like them.
Hey guys, could I just jump in for 1 second and say, I realized I made a tiny error in that chemistry piece. It's that I referred to the chemical with the symbol AS as astatine. It's actually arsenic. The symbol for astatine is AT. And so I sometimes get those two confused. So apologies to folks out there. If you look back at that balancing equation problem, the AS should actually be arsenic.
So if you were mixing the chemicals, you'd really want arsenic instead.
Arsenic instead of astatine. Not that anybody's using those chemicals, hopefully, but in any case.
Just in case.
All right, so we're going to take a few minutes. One of the things we do on the show is something called real-world apps. So we kind of talk about applications of math and science. And the one that we're going to show now is actually a new one. I believe Sam filmed this recently.
This is the aquaponics one.
I'm excited to see this.
Interesting.
All right, check it out.
Okay, we're here at the Grow House. My name is Sam Squilacci. We're here with Colorado Aquaponics, looking at an aquaponics growing system for real-world apps biology. All right, so tell us who you are and what you do here.
I'm JD Sawyer. I'm the owner of Colorado Aquaponics, and this is Flourish Farm here. And here at the farm, we raise fish and plants together in a natural ecosystem, providing food to the community and local markets and restaurants.
Explain, what is the difference between hydroponics and aquaponics?
Sure. Hydroponics, you're growing plants in soilless media, but you're typically doing that with either an organic nutrient solution or some synthetic type of nutrient solution. In aquaponics, we actually raise fish. And the fish, through their waste stream, are actually providing nutrients to the plants. So it's more of a natural ecosystem where one organism is providing and helping another organism. We don't discharge any water. We continue to recirculate that water. And that's important because we can grow a tremendous amount of food with a fraction of the water that you would otherwise use in traditional forms of soil-based agriculture or even in hydroponics.
What kind of sciences have you learned as you've gone through this process?
Understanding fish and their requirements, water quality, things that are toxic to fish, not toxic to fish, oxygen, flow rates, all these things that are necessary for the health of the fish, because we have to have healthy fish in order for this to work. And then certainly understanding the plant side of the house. What do plants need to thrive? Sunlight and nutrients and ventilation, airflow, all these different things. And then within that, there's the bacteria. That's the part we don't see as much, but it's critically important to this process too. And understanding their role in making sure that the fish waste can actually be converted to usable nutrients to grow plants.
JD, you just mentioned 3 different organisms. You mentioned plants, fish, and bacteria. And in biology, we talk about something called symbiotic relationships, right? Where each organism in the relationship provides a benefit for another organism. So how does that work in aquaponics?
Sure. Well, how about I take you around and show you how that works?
That sounds great. Okay, so JD, we're here looking at these different fish tanks. Tell me, what is going on here?
Right. So in this system here, we have fish. We're raising actually tilapia in this particular tank here. And the tilapia provide nutrients to the plants through their waste. So we regularly feed these fish, and they're doing their thing, pooping and producing urine. And that actually produces ammonia, among other things. And it's the ammonia that bacteria are actually converting into usable nitrogen or nitrate nitrogen for the plants. We do that particularly in this tank here. This is called a mineralization tank. And we capture a lot of that waste that comes through from the fish tank. And you can see all of these brushes here. These brushes actually help to capture and collect a lot of that waste and creates a home and a habitat for bacteria to help break that down into the trace minerals and elements that plants need.
The plant roots in the aquaponics system are actually just floating right in the water. Why is it that that doesn't create rot for the plant roots, or why don't the plants take up too much water? Why isn't that an issue?
Right, so in this particular case, we actually provide a great deal of oxygen, dissolved oxygen. We have little air stones that bubble up oxygen, and so if the roots are able to uptake oxygen, we don't have those types of issues that you mentioned. This is a little raft board here of bib lettuce, and you can actually see nice white roots is what you're looking for. If we were sending a lot of fish waste in here, these could get all brown and mucky, which would be a problem for the plants, and they would have difficulty getting the oxygen and the nutrients they need. But these have nice white healthy roots here, and they're getting a nice mix of the perfect temperature of the water, a nice balance of nutrients 24/7, and in that respect too, we get tremendous growth rates in aquaponics because they're getting nutrients all the time.
JD, there's been sort of a science focus in our interview today. I've been wondering about how biology relates to this, but what other school subjects might we be surprised that you would need to have a basis in to be successful in aquaponics?
Yeah, you know, there's a lot of different subject matters that are all integrated into an aquaponics system. Certainly the STEM subjects, science, technology, engineering, we do a lot of math here. There's defined relationships between the amount of feed and nutrient availability to plants that we mathematically figure out. From an engineering standpoint, we're dealing with water flow. So we've got hydraulic engineering, we've got structural engineering. You could go well beyond into the culinary arts, nutrition, economics, business subjects to really understand all of these things interrelate, particularly when you're managing a farm as a business, to understand how all these things work together in one farm. I can't think of any subject that's not somehow tied in to aquaponics in one way or another.
There's this old saying that you might have heard of, and it goes, if you give a man a fish, he'll eat for a day. But if you teach a man to fish, he'll eat for the rest of his life. Do you think we should change that saying so that we should teach a man to do aquaponics?
Yeah, absolutely. I mean, this is what it's all about. We are teaching people how to raise their own fish and feed their families, feed their communities. This is how we're going to change food production and make our planet more sustainable. So I love it.
Well, JD, I've really had a pleasure talking with you. Thank you so much for doing the interview today.
Likewise, it was a pleasure. Thank you.
Welcome back. Hopefully you found that as cool as we did. That was so cool.
Yeah.
Tell us what it was like being there.
It was just so neat. It's an amazingly cool operation, and as amazing as all the science was that I got a chance to see, the coolest thing for me was hearing about their mission. These folks are working in an area of Denver that is a food desert. The locals who live there do not have access to fresh food. They have to travel a distance to get to it. And this is a place that's selling to folks in the community these really healthy vegetables. And I just think that's so cool. You heard that bit at the end about him wanting to change the food system, and I love that.
That was very cool.
Yeah.
Well, we've got a caller on the line.
Excellent.
So, hello.
Hello.
Hi, thanks for calling Homework Hotline.
Yeah, sure.
Do you have a question for us?
Yes, I do actually.
What's your question?
Using the properties of water to explain your answer, why does sweat cool you down?
Yeah, that's a great science question. So this would probably be for a biology class or perhaps for an anatomy or physiology class. So in order to think about this question of why sweat actually cools us down, I think it's good to just kind of start by thinking about, do we experience this in our real life? So caller, have you ever had the experience of maybe your skin is wet for some reason, maybe you just got out of the pool, or maybe you got your hands wet from washing them, and then you feel breeze on them and your hands or your skin feels cool? Have you had that experience before?
Yeah, I believe so.
Yeah, so that's very similar to what's happening with sweat, and I think a lot of folks who I talk to about this think, you know, it's the water itself is actually, the water is cool, so the water is cooling me down. But in fact, what's happening is it has a lot to do with phase change. So water can take 3 forms. We have liquid water, and then in gas form, it's going to be called steam, and in solid form, we call water ice, right?
Mm-hmm.
Okay, so the way to think about it is this. When we want to turn water into steam, when we want to turn liquid into gas, what we're doing is we're putting energy into it to make that happen. So you can think of, for example, a pot of boiling water on your stove. Can you picture that?
Yeah.
Yeah, so what we're doing there is we're heating the water. We're putting energy from the fire or from the heating element on the stove to put energy into the water and effectively get it to change phase from liquid into gas. So when water changes, when a water molecule goes from being in liquid state to gas state, it has absorbed that energy that's going into it. Does that make sense?
Yeah, it does.
So when you are running, let's say it's a hot day, and you're running, your body produces sweat by essentially just excreting water out of your sweat glands. And what you've got is just a little thin layer of water on your skin. And the wind blowing outside and perhaps the sun shining on your skin is going to evaporate some of that water. And it's the same thing that's happening to liquid water boiling on your stove. Liquid water on your skin is going to change phase to gas, to steam. And that phase change requires an absorption of water, or of energy, excuse me. So the water has to suck energy from its environment. In the case of on the stove, it's pulling the energy from the flame or the heating element. But on your skin, it's pulling it from the environment around it. So this water would literally be pulling heat energy from your skin to change phase, and that leaves your skin a little bit cooler because some of that heat energy has been pulled away. Does that make some sense?
It does, yeah, thank you.
Yeah, and just for a little additional piece, if you think about going the opposite direction, to go from liquid water to solid ice, the opposite is happening. The water itself is giving up some of its energy. And so if you think about liquid water becoming solid ice, that environment, some of the energy inside that liquid water is going to escape to the outside environment, actually warming up the environment just a tiny amount. So it's really the opposite process happening. Make sense?
Yeah, thank you.
Cool. Any follow-up questions?
I think I'm good.
Okay, great. Thanks so much for calling in.
Thank you.
Nice.
Cool. I liked that question.
Yeah, it's a good one. It's relevant. Something
Yes,
we all
it's relevant.
experience,
That's
right?
a good way to put it. It's relevant. All right. Well, let's go back to Lily and see what questions we have on social media to answer.
So they asked to solve this equation, and it's 11 plus 3x minus 7 equals 6x plus 5 minus 3x.
I'll take this one, I guess.
Okay.
So I've got I just wrote the equation down that Lily mentioned on my screen. So here's our equation. In an equation like this, one of the things that we would typically almost always want to do as a first step, if at all possible, is simplify, meaning let's make this the easiest equation that we can before we start really working with it. So Nate was talking earlier about combining like terms, and that's one of the things that we can do to simplify. When it comes to combining like terms, we have to keep each side of our equation separate. So on the right side of the equation, I can see 6x and negative 3x. Now I can't combine those with anything on the other side of the equation. It's kind of a common error I see if that happens. So those two are like terms. Another set of like terms that I notice is 11 and negative 7. And I couldn't combine that with the 5 on the right side of the equation because they're separated by that equal sign. So that's going to be our first step, just to keep things simple. So the 11 and the negative 7, that together is going to give me 4. So I have 4 plus 3x on the left. And then on the right side of the equation, I can combine the 6x and negative 3x. So 6 minus 3 is going to give me 3. So I have my equation simplified. So that's typically your first step. That can also include distribution if you have any distributing to do. The second thing is, so our goal when we solve equations is to isolate our variable, get it by itself. But what you might notice here is that we actually have two, it's the same variable, but it's on two different sides of the equation. So what might be helpful is to get all of our variables to one side of the equation. Now it doesn't really matter which side, but just to collect them together would be helpful. So I'm looking at this 3x on the right-hand side, and I'm going to move it to the left side by subtracting it. And what you might notice is it actually, on both sides of our equation, our variables cancel. Typically at this step, if this happens, a lot of times I'll have students and they'll say, they'll think they did something wrong at this point. This kind of throws them off because we don't typically cancel on both sides. We're really just trying to cancel on one side, but sometimes this could happen. So I'm going to write the equation out with what we actually have left, and we have this equation, weird equation, that says 4 equals 5. When this happens, when your variables cancel, or you're solving and you're left with no variables, there are 2 possibilities. One possibility is infinite solutions, meaning it doesn't matter what x is, that equation is always going to be true. If you made x 5, the equation would be true. If we made it 1,000,000, it would be true. It doesn't matter what we made x, the equation would be true. That's for infinite solutions. The other option is no solution. And what that is meaning is that it doesn't matter at all what x is. Doesn't matter. It's never going to make that equation true. So at this point, when our variables cancel, we're going to be looking at what's left to help us to decide which of these 2 options is the case. Could x be anything or could x be nothing? And when you decide this, what you're really trying to decide is this equation true without my x's or without my variables? And well, does 4 equal 5? No, it doesn't. It never equals 5. So it doesn't matter essentially what our variable is. This equation will never ever be true. And so therefore what we would say is there's no solution to this equation. If we had something left when our variables canceled like this on the bottom right that I put on the screen, 4 equals 4, well, yeah, that's true, and that's always true. So if we had something like that, then we would say infinite solutions, but we don't have a true equation, so we have to go for it and say that there is no solution to this equation. So hopefully that helps. Those situations, they do happen every now and then. Not often, but they do happen, and it doesn't mean you did something wrong. Just know how to interpret your answer when you do the steps.
All right, so I think we're going to take a minute. As we mentioned before, we are sponsored by the Contemporary Learning Academy and Emily Griffith High School. So we're going to take a minute and hear a little bit about both of those schools.
Emily Griffith Technical College is turning 100 years old, and we want you to join in the fun. The Emily Griffith Foundation is presenting a year-long community celebration, opening doors of opportunity for 100 years. Here's how you can play a part.
Are you 1 in 2 million? Shop Automotive has donated a 3-year lease on a Mini Cooper that one lucky alum of Emily Griffith Technical College will win. All you have to do is sign up.
Go to egfoundation.org for more information.
Welcome to Nerd Necessities Network. You're probably thinking, what is Nerd Necessities Network? That's a good question. Nerd Necessities Network is a premier DPS TV show all about nerdy people, places, and things. You can check us out on Facebook and YouTube and all the social networks. That's a wrap!
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. Never mind from when, why, or how.
'Cause now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
Welcome back. Hopefully you learned a little bit about Emily Griffith. there's a lot to offer at Emily Griffith. I can say that about Emily Griffith. I'm sure CLA is the same. I don't want to
CLA
put
is
down
wonderful.
CLA.
There's so many good things, but Emily Griffith seems great.
It's fantastic. I have a lot of good things. We have a lot of good things to say about it. So if you are interested, check us out. There's a lot to offer. Well, one of the things that we do on Homework Hotline is we like to post things on our Facebook page that are educational or interesting to us. We're always about learning and learning new things, and so we've got some interesting stuff on Facebook now. Lily, would you share what we have this week?
So this week we were talking about the history of the cowboy hat, which coincidentally is not that old, to be honest. But before cowboy hats ever came into play, usually what they would call cow punchers, never heard this term, but they would actually wear anything from top hats to actually old war hats, Civil War headgear. So, and sailor hats also. So I thought it was pretty interesting that until John B. Stetson, pretty sure that's how you say his name, came along, there were pretty much you could just wear anything, but now they're a cowboy hat. So, yes. So, yeah.
Oh, fascinating. Well, it's interesting. So the Stetson hat has not changed in style since it started. In 1865, the construction of the hat is still almost the same, which is really interesting. And I guess I've always thought of the cowboy hat as a sort of a fashion item. I guess that's because of the time that I live now. But you know, it is a really useful hat in a lot of ways. So there's this story, and I don't know exactly how true it is, but there's this story about John B. Stetson being out on a hunting trip with some people, and he wanted to impress the people and show them, hey, I can make a blanket without weaving anything. And you know, they had a dead animal, so he skinned the animal and made a blanket out of the fur. And then apparently, as an additional way to kind of show off, he made a wide-brimmed hat, supposedly as a joke. Like the brim was just supposed to be overly ridiculous for its size. But once it was made, people said, hey, you know, this wide brim, it's protecting me from the sun, it's protecting me from the rain, and all the other, you know, elements that come at me as a cowpuncher. So that's
yeah, I mean, it was very functional, and that's what made it catch on, is how functional it was. So the high crown of the hat, it provides insulation to the top of the head where most of your heat is lost. So basically you're losing heat through your head, and it's basically insulating the heat in your head. So it's keeping your head warm, number one. And then it also has the wide brim, so that gives you shelter from sun, rain, snow, whatever you might encounter. And then it's also waterproof. And so not only does it protect you from the elements, but you could carry water in it. So they could fill the top of the hat with water and, you know, give water to their animals, or they could drink water from it and carry water with it. And so it made it really, really functional, which is why it caught on so quickly and why it's still around.
Yeah, I think it's interesting to actually think about the origins of the hat, because like you mentioned, Sam, when you think of cowboy hat, you just think like, yeah, that's just a cowboy hat, but it didn't exist before, and it was made in 1865 and John Stetson actually started with $100. He rented a small room, bought all the tools he needed, and bought $10 worth of fur, and a year later he created what's called the Hat of the West, and it's now the famous Boss of the Plains hat, which is just really fascinating because, you know, everybody thinks cowboy hat, they think Stetson, and he started with $100, and these hats cost like $70 to $80 each now, like almost as much as his initial investment. So it's pretty fascinating how popular. When the original Stetson was about a $5 hat.
Yeah, I mean, startup costs for a business in the mid 1800s are way
much lower
than they are today. I would almost start a business if I lived back then.
Shows if you make something well,
right,
it'll stick around.
Positively, it will.
For sure. Well, I hear we have another caller, so let's take that. Hello?
Hi, so I have a math question.
All right.
Oh, great. What's your question?
A 3x4 rectangle is inscribed in a circle. What would the circumference of the circle be?
Oh, I can take that one. Geometry
Okay.
question. I'm going to actually just go ahead and sketch one. Are you watching right now?
Yes.
All right, so I'm going to go ahead and try to draw that. So what we should know is a rectangle inscribed in a circle is actually going to be, let's see how this turns out, something like this, right? Where all four corners of our rectangle touch the outside of the circle. So when you said the measurements of the rectangle are 3 feet by 4 feet?
Yes.
Okay, so I'm going to go ahead and label that. Now, and you're looking for the circumference of this actual circle, right?
Yeah.
So do you remember the equation for circumference of a circle?
Not sure.
Okay. So that is actually the circumference is pi times d. And I'm going to kind of go off track here for a second. Do you know what pi means or what it represents?
It's an infinite number.
It is, and I think that's mostly what everybody knows about pi. But pi, do you know what it represents?
It's a ratio.
It's a ratio, right? So pi is actually, because everybody always forgets these equations, it's actually a ratio of the circumference to the diameter.
Yeah.
Which, if you do this calculation, if you punch in your calculator, you get 3.1415. And like you said, it goes infinitely. So the interesting thing about this, it doesn't matter how big or how small the circle is. You can talk about, just a giant circle. You can talk about the smallest circle you can imagine, and this ratio is true. So when we talk about circumference, if you actually solve this for circumference, and I'm doing this kind of quickly, that's how you get the circumference is pi times d. So when we're looking at this problem, we actually need to know the the diameter of this circle. But right now, all we know about is the measurements, the dimensions of this inscribed rectangle. Well, the other thing that you should know about this is that when we have a rectangle inscribed, the diameter or the diagonals of this go straight through the center of the circle, right? So and I'm going to erase one of these to make it a little simpler, but we have the center right here, right? So what are all the angles of a rectangle? Like, what's the measurement of all the angles? You still there?
Oh, what?
So a rectangle has all the corners. What are the angles formed? Do you know what the measurement is?
Go no.
Okay, that's all right. So it's a 90-degree angle. So we have basically what we have here is two right triangles. And we need to know this diameter across the circle. So when we have a right triangle, if I know two of the sides, we can use our a squared plus b squared equals c squared.
Pythagorean theorem.
Pythagorean theorem, and solve for that diagonal, which is what we really need. So in this case, we'll say 3 squared plus 4 squared equals c squared. And then we simplify and we just solve for c. So we get 9 plus 16 equals c squared. And we just continue solving, and you end up with c equals 5. Is that making sense?
Yeah.
Okay. So now you know this entire diameter from here all the way over here is 5. We know the circumference is pi times the diameter. So the circumference of this circle is going to be 5 pi. Or if you did it in your calculator, I don't know, it's going to be approximately 15.70 something. Does that make sense?
Yeah.
All right.
Thank you so much.
Thanks for calling.
I like that, where you kind of worked backwards. You're like, okay, to find circumference, I need these pieces of information. So how am I going to find those pieces of information? That's good.
Which I think is a good way of problem solving. I think sometimes you read a problem and it's really confusing, but once you draw everything out and you start working through it, then it makes a lot more sense.
I know this, I don't know this. How do I find it?
And the origins of things like pi, so it's not like there's just this number that math teachers give you and you have to use it to find this stuff, but it comes from a certain place.
There's a reason for it, yeah.
Not just made up.
Well, if you are just joining us or just joined us, one of the things we do is we ask a trivia question, and you have a chance to answer it and call in and get a prize. And just to give you a chance, in case you missed it at the beginning of the show, our trivia question today is, which state has the most dairy cows? So if you think you have an answer, or if you have an answer, give us a call. The phone number's on the top right of your screen, that way I guess. top right of your screen, 720-424-1666. Just give us a call within the next few minutes and you can get a prize. In the meantime, let's go back to Lily and get some more of our social media questions answered.
So we have a science one, and it asks, what does the pancreas do?
Sure. Okay.
Insulin?
Cool. Yeah. That could
Something
just
like
be the
that.
answer right there.
Done. Move
That could just be done.
Next.
Maybe to like,
You know more than I
I'm
do.
going to add a little to that, but effectively, Becca's answer is exactly right. When you hear pancreas, you should think insulin. Pancreas, insulin, they go very well together. Okay, so pancreas is a gland in your body. And to just complicate things a little bit, there's another gland in your body called the hypothalamus. And the hypothalamus is often regulating what happens with the pancreas. But essentially, the pancreas is responding to blood sugar levels. This is the simplest way to think about it. So when you eat any kind of carbohydrate, simple sugars or complex sugars like starch from potatoes or rice, your body is going to break that down into a form of sugar called glucose that will enter your bloodstream. So you can have glucose flowing in your bloodstream, but the levels of your blood sugar can affect different things. So you don't want your blood sugar to be too high because that can actually be toxic. And you don't want blood sugar to be too low because that can lead to low levels of energy. So essentially, what the pancreas does is produce, well, it produces more than this, but two main hormones, insulin and then this other one called glucagon. The pancreas produces insulin when you have a really high level of glucose in the blood. And insulin's job is to take that glucose and move it out of the blood. And insulin can move it to a few places. Insulin moves glucose to your liver, where it's stored as something called glycogen, also to your muscles, where it's stored as something called glycogen. And then insulin can even initiate a process called novolipogenesis, which is the formation of fat tissue, adipose tissue, from blood sugar. The other really important hormone that the pancreas produces, which is not given as much attention as insulin, is glucagon. And glucagon can do the opposite. If you have too low levels of blood sugar, glucagon can make glycogen from your liver or your muscles available to your bloodstream as glucose. So if we can imagine what your body wants is to have this sort of regulated, stable level of blood sugar. Insulin's job is to take it when it's at a high level and bring it down. Glucagon's job is to take it when it's at a low level and bring it up. And the pancreas is simply the part of your body that makes those two hormones. Does that make sense?
Mm-hmm. That was a whole lot better explanation than mine.
Oh,
Mine
well, no,
was
insulin is the right
And
answer.
insulin.
If we were
And
looking for
glucagon.
one word, and glucagon. Right?
Yes, now I have two words
No,
to do
insulin is the one.
Thank
That is
you.
the right answer, Becca.
Like it.
Yep.
So wait, you don't have to have a pancreas. You can live without your pancreas. It's just, it's
So
nice
yes, you
to
can,
have
you can,
one.
but there's only two ways to live. So if you have no pancreas, that means that if you take in carbohydrates above any basic level, what's going to end up happening is, on here we've got a pancreas on the screen right there for you guys to look at. If you didn't have a pancreas, you couldn't produce insulin, and so essentially, or glucagon, so you can't really regulate blood sugar.
So would you take
So you've got to be
insulin
really
shots, or-
good
Well,
about
two
regulating.
choices. One is you could just not eat any carbohydrates.
Okay.
You could live
seems
entirely
sad.
off
Really
of.
like that,
you could
but-
live entirely
Sounds
off
awful.
of fats and proteins.
Mm-hmm.
So you just basically at this point, all you're doing is eating meat and cheese and drinking milk and water. Is fine.
So you'd be very fit without a pancreas.
Yeah, and some type 1 diabetics are if they follow that diet.
Yeah.
The other option, and the more common thing that we do here in the United States in the modern world, is we say, oh, you don't have a pancreas? Well, here's some pig insulin. Inject that into you, and so you're sort of an external pancreas for yourself.
Mm-hmm.
So if anybody out there knows somebody who has type 2 diabetes, it's very common for type 2 diabetics to give themselves insulin shots. And what they're doing is a type 2 diabetic has a pancreas that's no longer functioning, and they're providing insulin to themselves because they don't have that pancreas to create it, and the insulin just does the job. And one incredible thing is that pig insulin mimics human insulin very, very well. So that's where a lot of our insulin comes from. So those are your two options if you're pancreasless.
Gotcha.
What if you're like my dad, and my dad's type 2 diabetes, but also is hypoglycemic? How does that work out? It's either hyper or hypo. I'm not really sure the difference, to be honest. He gets low blood sugar, so he has to eat sugar in order to have energy. Yet he has diabetes, so he can't eat
too much sugar. And, and type 2
so
diabetes
it's like, how
is
does that
developed
work out?
over your life. I mean, so your dad just has to kind of hit a sort of
Sweet spot.
Sweet spot, and really you don't need that much sugar to be
Yeah.
at a healthy level. One of the big problems we run into is people are eating simplified forms of sugar. So if your father is eating a lot of like white sugar, white rice, easily digestible sugars, that's going to spike the level of blood sugar quickly, and it's going to need to be taken care of quickly. But, and your dad probably knows this, if he's eating things like whole grains, whole grains are going to be a slow release of that simple sugar because it's a larger, more complex sugar molecule called starch that has to be broken down. And that slow release is going to be healthier for a guy like your dad. Have your dad look into something called super starch. Super starch is a special starch developed in a laboratory, and the idea is that it's ultra slow release. So you can eat a starch and you get a very slow trickle of blood sugar, which can be really healthy for diabetics.
Oh, nice. Awesome. I will
Super
keep that in
starch.
mind.
Super starch.
Good to know.
Yeah.
Very cool. Well, let's get that trivia question answered.
Nice.
So one more time, what was the trivia question, Lily?
So the trivia question, one more time, was which state has the most dairy cows? And that was California, if you guys watch commercials at all.
Not my guess. That was
Yeah, I
not
don't know.
my
I
guess.
would have guessed Texas. I don't know why. They just have a lot of cows there, but I guess
Everything's
different
bigger
purpose.
in Texas.
So I heard that there are more cows in Texas, but they're beef cows,
Right.
not dairy cows.
Yeah.
Right.
See, I was thinking Wisconsin.
I was
is
right
what
with you.
I
Oh,
thought.
right, 'cause of the cheese
That's what I
heads.
thought. I
Is
thought
that not the
Wisconsin,
famous-
and then I thought it's got to be somewhere in the Midwest. I don't know, with lots of land.
Yeah.
But
Well, it's
the
expensive
in
in
order,
California.
And
so
water.
second is Wisconsin, and then third is New York, fourth is Pennsylvania, and then fifth is Idaho. So those are the next five, or the next four, I guess, in order from most to least. And then there are also dairy farms in all 50 states. So every state has dairy farms in it.
Live in Alaska, huh?
Even Puerto Rico.
And
Isn't that a
Puerto
state?
Rico. Yes. Yes, yes, yes. So because in the spirit of dairy farms, we've learned some things about dairy farms. What have you learned?
You know, one of the things I learned, which since we were talking about the pancreas, is that a lot of people think that a cow has 4 stomachs, when in fact it has 1 stomach with 4 chambers inside of it. Something I found interesting.
Okay, yeah, that would be kind of strange to have 4 stomachs. Make a lot of sense.
Do you guys know why they have 4 stomachs?
No,
Do you have any
why?
ideas on why they need them?
Tell us.
So it has to do with the fact, well, so cows eat, a lot of what they eat are grass and plants that if you or I ate them, it would make us fairly sick. And if you've ever had the experience of eating grass or knowing maybe a little kid who eats grass, what tends to happen is they either throw it up, or if it passes as almost whole grass. So there's a compound in plants called cellulose that our bodies really just do not have the ability to break down on a large scale. Cows have these 4 chambers because essentially what's happening is they're like little fermentation chambers with lots of bacteria living in them. And it's like a slow transition of this.
So they're just breaking them down.
Yes,
little
and
by
it's
little.
like stages. It's like extra stages of breaking down food. So cows can break down more complex sugar molecules or starch molecules than we're able to, which is good for them since they live enough grass.
So really just it's slowing down that process a lot.
It really is slowing down the
Giving it
process.
4 chances to digest rather than just 1.
More opportunity for bacteria to work on it.
Makes a lot of sense. Yeah. Makes a lot of sense.
What else?
I learned that, dairy farms are really good for our economy. So kind of going away from the biological aspect of it, getting into economics. When a dairy farmer sells $1 of milk, it's generating $3 worth of economic activity. And every $1 million of U.S. milk sales are generating 17 jobs. So it generates a lot of jobs, creates a lot of economic flow. It's really good for our economy in America.
That's interesting, I guess, because you just think of like producing milk with a cow, but then you have to ship it, you have to store it, refrigerate it, you have to make the containers.
And then
That's gonna be quite a bit.
distribute and sell it in grocery. So there's a lot going on with selling the milk. And so every $1 that the farmer makes, there's $3 being, I guess, transacted, you would say.
Which the U.S. sells 23 billion gallons of milk annually, so that's like
Whoa, that is so
a lot
much.
of
Crazy
money
amount of milk.
off of
Is that
just
in the
milk.
U.S., you said?
That's annually, yeah, in the U.S.
Maybe we
23
export
billion
some
gallons.
stuff.
And you figure, so each of those gallons of milk,
Yeah.
how much are they selling for? Like,
$4.
what,
And then
$4?
21% is just from California.
Wow.
That's crazy.
Wow.
Oh, man.
You know, what's really wild to think is that California has a major drought going on right now.
Yeah, that's true.
And it takes, according to what I just looked up, 2,000 gallons of water to make 1 gallon of milk.
I just saw Mad Max
So
last
it's
night,
basically-
and it was they were all drinking milk instead of water. I don't know. I fell asleep during it, so I don't really remember. But I was like, oh, that's my world. I love that world. I love milk. But all right, well, that's pretty much it for our show for today. We're so happy to be back. We will be back again tomorrow, so check us out again tomorrow from 4:30 to 5:30. Send your questions in, and we'll see you tomorrow. Thanks, guys.